Right. So my name is Zach Shurab-Conti, and I'm a research associate at the Alan Turing Institute here in London. And I would also like to introduce my colleague and co-organizer of the seminar series, David Mazagur, who is a PhD enrichment student here at the Turing. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. For the benefit of those joining us, and for the very first time, I'd like to sort of briefly introduce the topic of the seminar series, which is, again, physics-enhanced machine learning, for focusing primarily more on engineering applications. So physics-enhanced machine learning is this upcoming subfield in machine learning and deep learning that aims to incorporate our physical understanding in the data-driven machine learning process. On a side note, if any of you would like to join any of our upcoming seminars or present at our upcoming seminars, we really encourage you to get in touch with us, to book a slot, and share your work with our growing community. And as for the format of the seminar series, our speaker today, Shams, will share his work for around 40 to 50 minutes, followed by Q&As, which you can do so either by typing into the chat or by unmuting yourself and asking in person. All right, so without further ado, I'll ask my colleague David to introduce our speaker for today. And with that, I thank you all.
Yeah, hello everyone. Thank you for joining us today, and especially thanks to Shams for offering his presentation to us. So Shams Basir is a PhD student in the Mechanical Engineering and Materials Science department at the University of Pittsburgh. He holds a dual baccalaureate science degree in aerospace and civil engineering from the Middle East Technical University. His research interests include scientific machine learning, optimization, high-performance computing, and computational fluid dynamics. So, yeah, I hand over to you, Shams, and yeah, we look forward to your presentation.
Hello, everyone. Thank you, David. Thank you for inviting me. This is a joint work with my PhD advisor, Inaj Shanajak, and our area of research is basically an understanding and simulating phenomena that involve some sort of transport of heat or fluids. And these phenomena are governed by partial differential equations, and these partial differential equations are nonlinear and very complex to solve. So state-of-the-art methods for the solution of these PDEs are mesh-based numerical methods that you might be familiar with, such as finite difference method or finite volume or finite element. So the whole idea is that you discretize your domain into grids or meshes, and then you solve your PDE on those nodes. However, there are some challenges in these methods, like mesh generation could be very tedious and time-consuming, and the solution could be only obtained at the specified nodes. So once you have your mesh, you can only get the solution at those nodes. And if you want the solution at a different node, you either have to interpolate or create a new mesh and then solve the whole thing all over again. And in case you have moving boundaries like wind turbine or helicopter blades and things of that nature, then you might require regridding. And in cases where boundary conditions are known at partial location, then this method could be, like these conventional methods, could be challenging to implement. And for inverse modeling, these conventional methods are also inefficient. So an alternative approach is to use artificial neural networks. So artificial neural networks are shown to be universal approximators. That means that they can represent any bounded continuous function with arbitrary precision. And they can also be viewed as mesh-free methods. So that's a very a good thing, that we do not require mesh for these methods. And once you train these models, then the solution could be obtained at any point in the domain, unlike conventional numerical methods where you needed to solve the method on a new mesh. And solving inverse problem could be as efficient as solving forward problems with artificial neural networks. And so there's a historical perspective on machine learning. Actually, the root of artificial intelligence and machine learning could be traced back to like centuries, as you could check out in these two references by Wang and colleagues, and Schmidt-Huber and colleagues. But modern machine learning started in the 1940s, and it had some ups and downs. And they're mainly for learning paradigms in machine learning, like supervised progression, supervised learning, for example. So the idea in supervised learning is that you have a set of inputs and outputs, and you're trying to learn a general rule or a model that's mapping these inputs to these labels. And these labels are supervised labels or exact labels. That's why it's called supervised learning. And unsupervised learning is where you do not have these labels, where you're trying to extract patterns from your data. And semi-supervised learning is a hybrid of the two. And another learning paradigm known as reinforcement learning is where you are trying to learn an optimal policy by interacting with a dynamic environment, and you're reinforcing your knowledge as you're interacting with this environment. And so here is a high-level overview of neural network. This is a toy network, and for the sake of simplicity, I removed biases. And this network has like one hidden layer, one input, and one output with two weights or parameters that are represented as theta and omega here. And so to get the result from this network, we have to pass one, we have to do a one forward pass through the network. And so these forward pass is nothing but a series of arithmetic operations. So for example, here we have an input X, we're sending it through the network, and it gets multiplied with the weight theta, and we get an intermediate variable A, and then we send it through another nonlinear activation function denoted as F, and so until we get U hat, which is the output of the network. But the idea here is that you want the output of the network, which is U hat, to be as close to your exact or supervised label as possible, which is denoted as U in this case. And so one way to do that would be to define an objective function or a loss function, which is calligraphic L in this case, which is nothing but a quadratic loss function. And now all you want to have a very small loss function that would show that, okay, for that input, your model is giving a very close approximated solution to your supervised label. Now, this is a nonlinear optimization problem. And so you cannot find solution directly for theta and omega. So what you do is you resort to gradient descent type optimization algorithms. And for that, the whole idea is that you want to tweak these theta and W and omega such that the output of the network is as close to you as possible. And for that, you need gradients. And for gradients, you do chain rule. You use chain rule in calculus. That's pretty famous. I mean, we all see it even in high school, I believe. And the idea here is that you want to reuse the calculated gradients as you go down the network, and that's called dynamic programming. And these packages like PyTorch and TensorFlow are mobilized with these packages, and they do this automatically for you. And these are some of the common activation functions. And for our problems, because we have PDEs like derivatives and stuff, we use sigmoid and tanh hyperbolic a lot because they're smooth and differentiable. And like I said, once you have your objective function down here, in this case, calligraphic L, then it's nothing but an optimization problem, and you could use your optimizer of choice to optimize for thetas. So speaking of that, here I want to talk about supervised learning because this is where we start comparing our physics-based models with. And the idea here is that you have a domain represented as omega with its boundary conditions, what's boundary partial omega, and you're given points or data in this domain. And the idea is that you want to find a model that's calligraphic N, in this case, which is a neural network, that is mapping these coordinate locations, which is X on this domain, to its solution. And so we purposefully divided the objective function for this problem into two parts, which is calligraphic sub partial omega that represents the loss function for the boundary, and the colored or the highlighted loss, which is the objective function for the domain. We did this on purpose so we could compare it and show how easy it is that you could switch the loss function for the domain with the physics, and now you have a physics-based or physics-informed model. And like I said, now in physics-informed neural networks or physics-informed or physics-based models, you do not have labels for the domain. You have some function, some relationship, some kind of PDE that the output of the network you had would satisfy. And so all we did was just switching the objective function for the domain, which is calligraphic L sub omega. Now we will see that this approach is not new. It has been there for like quite some time. For example, in 1994, even though this paper is not known in the community, but I wanted to show that these approaches have been there for quite some time. So, for example, in 1994, Dissanayake and colleagues proposed this method where they, let me get this thing out of here so I can see. Anyway, I don't want to mess it up. So they had this differential operator, which is calligraphic L, with a boundary operator presented as calligraphic B in this case. And so all they did was they were like, okay, we have a loss function for the boundary and we have a loss function for the domain, and we're just aggregating them together into one objective function and then training a neural network on them. And so back then, we didn't have TensorFlow and PyTorch and all of these autograph packages. And so what they would do is they would use chain rule and calculating all of those derivatives by hand. And that would kind of like take the flexibility away, because if you use, let's say, three hidden layer neural network, then, and if you switch it to 4-layer, then you have to do all that calculation. So back then people didn't know a lot about neural network. And so a lot of people didn't appreciate these approaches. And around the same time, or probably a year later, Van Milligan and colleagues also proposed a similar approach. They had a loss function for differential equation and a loss function for boundary condition, and they aggregated them together to solve into an objective function, and they trained a neural network. And so these approaches have been applied to several problems like Schrodinger equation and Berger's equation, that you could check out a paper. Like, we have a long list of problems that these methods have been applied to. And so in 2003, Parisi and colleagues also used neural networks, and so this is they used like a mean of an average of like losses on the boundary and on the domain. And so this is exactly what's known as PINs today, or maybe physics aware neural networks, or any kinds of like physics-based models that you see today. So you see that these models have been there for quite some time. And different from these works, Lagares and colleagues proposed a different approach, where they said, well, we don't want the objective function for the boundary and for the domain to be aggregated together. We instead want to create a trial function, which is psi sub t in this case, that's satisfying the boundary conditions automatically. And so this is good, but it has its own limitation. For example, if you know the boundary condition at sparse location, then it's very hard to create trial function. And if your domain is complex, then again, it's not easy to create trial solution. And so the whole point of using neural network was to not impose our own biases on how the solution should look like. So when you're creating a trial function, you're basically imposing your own bias. And so it would be hard to know what is an optimal trial solution for this problem. For example, here I show like a simple one-dimensional Poisson equation with homogeneous boundary condition. You could create infinitely many trial solutions, as I have shown on the right, and you have no way of knowing which one of these are the best solution for the problem you have. And like I said before, modern implementations of physics-informed neural networks are the one by you and colleagues known as deep rich method, and by Raisi and colleagues known as physics-informed neural networks, which is popular. That's why I adopted physics-informed neural network name for my slides. and deep Galerkin method by Serignano and colleagues. So like I said, the whole idea is that you just switch the domain loss with a PDE or some kind of like functional relation that you have, and you create a mono-objective function. Now, notice that the scales are different for the boundary loss and the domain loss. For the boundary loss, you could have Dirichlet boundary condition or Neumann boundary condition. But for the domain loss, you have physics. You could have second order differential equation, third order differential equation. So the scales are different. So this is a really, I should say, crude way of formulating an objective function, because these two objective functions does not share the same scale. So it's like apple and oranges summed up together to give you either orange or apple or both. So, and you saw that those formulation from the 90s, the issues from the 90s carried over to modern implementations. So these modern implementations are the same thing, but they're using TensorFlow or PyTorch or these new packages. And we showed this in our paper in AIAA SciTech. We showed that, well, if you have a pure regression model where you do have labels compared to physics model, for a simple one-dimensional Poisson equation with sinusoidal solution, we use sinusoidal because it's easy to make the solution complex so you could analyze them. And so you see that when omega is 5, you have a very simple solution. Then PIN model is producing 2 orders of magnitude better solution than a pure regression model. But when you increase the complexity, PIN model is failing, whereas regression model is keeping its accuracy levels. And so we wanted to see why that happened. And we looked at the loss landscapes, and it turns out that loss landscapes for purely data-driven or supervised models are very smooth and nice. Whereas for PIN model, when you increase the complexity, these landscapes gets chaotic and very, very, very complex to solve. And we do know that the only thing that we changed between the regression model and the PIN model was just adding physics. And it changed the scales between the two objective functions. And so turns out that people realize that, well, these two losses doesn't share the same scale, so let's multiply them with some multiplicative weighing factors, which are shown in red here, lambdas. But the question is, what are those lambdas now? Well, in conventional machine learning, often we have something called validation data set. And so validation data set is used to tune these hyperparameters. But in our case, we do not have the luxury to have validation data set. And so there's no way to know what are these lambdas. And if you don't know the solution, then there's no way of knowing what these lambdas could be. And here, I want to discuss 2 methods that's published, and I show like how the problems and the issues with those methods. So this is a method published by Wang and colleagues, and they call it empirical learning rate. And so their idea is that, well, if you have an objective function like given in 1, what you want to do is you want to find or tune those lambdas like the one given in equation 3. But the issue here is that updating these lambdas in equation 3 does not necessarily satisfy the optimality condition. And so what's optimality condition? We know it from basic calculus that if you want extrema in a function, maximum or minimum, the derivatives have to satisfy 0. So that's the necessary optimality condition. And so if you update your lambdas like the one given in equation 3, then you're not necessarily satisfying the optimality condition. But what's the consequence? The consequence is that your optimizer might just land somewhere in the loss landscape, and you think that that's a local minima, but it's not, because fundamentally your objective function, the way you're updating these lambdas, are not satisfying the optimality condition. Another issue is that if you look at equation 3b, when these losses get smaller, this lambda hat is growing unbounded. That means that your global learning rate is growing so large that when you're approaching some local minima, you're overshooting. And another issue would be that for these lambdas, you can see in equation 3b, you need the gradient of each of these loss terms with respect to the gradient of the parameters of the network with respect to each of these losses. And that means that if you have m loss, you have to do m backward passes to get the gradients, and then update these lambdas, and then do another backward pass to get the summation of the overall thing. And so that's kind of like computationally expensive. And we even discussed it in our paper for people who are interested. And another approach is to say, well, we want to somehow heuristically learn these lambdas. And the idea is that we want to do an affine combination. That means that these lambdas are between 0 and 1, but their summation is overall 1. But we said before that these lambdas, these objective functions, do not share the same scale. So if they do not share the same scale, then an affine combination would not be a good objective function, because then you no longer, these lambdas no longer represent which objective function you're favoring, because they don't share the same scale, so they're not the same thing. Let's say you say you want a 70%, you want to focus, let's say, on the loss for the boundary. You think you're focusing 70%, but you're actually not, because they don't share the same scale. And so later on, we will use some of the benchmark problems that that authors van der Meer and colleagues studied, and we show our method against theirs. And another approach is curriculum learning. So this is in machine learning applications. It's easy because you have data, and what you want to do is you want to expose the model to simple training data, the first or the early stages of training, and then you start increasing the complexity as you go. And Aditi and colleagues adopted that approach for training physics-informed models, and they were like, well, we could start with simple solutions and then increase the complexity. That's fine, but then we don't have data. If you, let's say, for Poisson equation, you're giving me the boundary condition and the sourcing term, I don't know how the solution would look like. So there's no way for me to know, like, okay, what's a simple solution for this type of problem or for this type of solution? So there's no way, and that's a challenge. And they use this pure this original formulation, which we showed is not a good formulation, because these objective functions are not sharing the same scale and all of that stuff. So our objective here is to find or to develop a framework that's precluding these manual hyperparameter tuning, and that's producing consistent result. Means that if you train it like 10 times, you shouldn't be getting 10 different results. You should be getting consistent results. And the solution shouldn't be physically unfeasible, or like, let's say you have your temperature is 100 degrees overall your domain, and all of a sudden you're getting 5,000. So whatever you're getting, the solution shouldn't be unfeasible, and it should be robust to noise. If you have noise in your data, you should have a way to handle that. And the solution shouldn't be dependent on the mesh size, and you should have the capability for one-shot super resolution. That means that if you train it on your data for any fine meshes, you should be able to get or at least hold similar L2 norms and errors. And also, forward and inverse problem with multi-fidelity should be handled in a unified fashion. So this is our objective. And for that, I would like to discuss nonlinear constraint optimization here. So the idea in nonlinear constraint optimization is that you have an objective function, which is calligraphic G, and it's subject to some constraints, which is calligraphic C. So what you want to do is you want to convert them to unconstrained optimization problems, like the one given in 2, 3, 4. And for that, you have these 3 methods, like penalty method, a Lagrange multiplier method, or augmented Lagrangian method. And so these methods are discussed in detail in these 2 books that I have mentioned. So I don't want to get into details of these methods for the sake of time, but people who are interested could look this up. And in our work, we're using augmented Lagrangian because this is keeping or combining the merits of penalty method and Lagrange multiplier method. So if you look at equation 4, you get rid of lambda, you're getting penalty method. You get rid of mu, you get Lagrange multiplier method. And now we're moving on to to formulate our constraint optimization problem. So we say, well, we have an objective function, which is calligraphic G sub f, and f comes from that functional relationship. It'll be clear in a bit. So and we want this optimization problem to have these constraints like calligraphic B, which is our boundary operator, to be within some small range. And that means that if you're off like minus epsilon or plus epsilon, you should be good on the boundaries. And now one could say, well, why don't you take absolute value of B and make it smaller than epsilon? Well, you could. And so without loss of generality, we said, well, let's say that's a phi. And phi is nothing but a convex function, a positive convex function. And with the minimum of phi is basically the minimum of B. So if your B is 0, phi will give you 0. So you're good. And now it's a general distance function. We call it distance function. And so because this is a positive distance function now, if you push epsilon to 0, you get your equality constraints. And now we have our equality constraints. And later on, I'll show why this phi is important. So for example, here we say, well, let phi be an identity function. Well, that means if phi, basically whatever input you're putting to phi, you're getting the same output. And so the issue with that would be that once you take the gradient of that loss function with respect to the parameters of the network, then the error, which is u hat minus u, that information is lost. But if you use phi like a quadratic function, then you always have a mechanism to backpropagate that error that you made on the constraints. And so that's nice. And we also showed this in our paper, how they perform with different L2 and L infinity errors. And now we're coming to our formulation here. And so here we're trying to combine an objective, we're trying to formulate an objective function for when you have clean high fidelity data or noiseless data, or when you have noisy measurement data. So noisy measurement data here is the objective function for noisy measurement data is represented with calligraphic G sub m. And that's nothing but a maximum likelihood estimation. And so that epsilon, do you guys see my mouse, by the way?
Yes, yes.
Oh, great. So here it is. So this is the maximum likelihood objective function. So this epsilon, the sigma, basically, this is the variance of the measurement data. And if you have a very sort of clean data, this variance would be small, and then you're putting more weight on your data. But if you have very noisy data, this epsilon, this sigma would be very large, and then you wouldn't have a lot of weight on your data. And this constraint is we're assuming that your boundaries are 100% accurate or clean. If in case your boundaries are noisy, then you could add this to your noisy measurement loss. And so GF as the objective function for the PDE, and then you could convert this constraint optimization problem that's given in here to an unconstrained objective function that's denoted as calligraphic L. And these lambdas are now updated properly by the augmented Lagrangian method. And you no longer have that issue of scale problem and all of that. And so whatever you're getting, the results of this optimization problem would be a solution you had, which is satisfying your constraints, your boundary constraints, and it's combining the information from your measurement data and your physics. And to evaluate our model, we have these two metrics, which is relative L2 error and maximum absolute error. And so now we're using that same old 1D Poisson equation with the same hyperparameters, same network optimizer and all that stuff, with just a change of objective function. We see that as you increase omega, PECANN approach is producing 3 orders of magnitude better solution than PIN and 2 orders of magnitude solution better than regression model. And for omega 15, PIN is failing and PECANN is producing one order of magnitude better solution than pure regression model where you have labeled data. And so now we're looking at loss landscapes, and you see that a pecan loss landscapes is way smoother and easier to optimize than PIN model as we increase the complexity of the solution. And here we want to show pecan on a very irregular problem to highlight that this method is applicable to very irregular domains. And we show here that it produces 3 orders of magnitude better solution than a conventional PIN approach. And here we're trying to tackle a multi-fidelity problem. And so this problem is studied in Meng and colleagues. They proposed some composite neural network where you had a network for low fidelity model and a network for high fidelity model, and somehow you're connecting these two and you have hyperparameters and all of that stuff involved. And so we show that you only need one model, and but you have that, but you need to combine or formulate an objective function that is combining information from measurement data, low fidelity, high fidelity, and all of that into one objective function. And you could train one simple model and let the network discover those information instead of us manually combining information from low fidelity and high fidelity data. And so here we show that with actually one network, given the pressure head in the soil column, which is H here, you could easily learn KH, which is soil conductivity here, with your multi-fidelity and high fidelity models easily. And the error levels are showing here like 22% for our reference, which is Meng and colleagues, and 2.58% for our work. These slides are the ones that that we haven't published yet. And so we show here that actually noise in the solution is corrupting the backpropagated gradients. And what that means is that when you're training your model, your solution is not accurate. Especially during the early stages of training, your solution is noisy. And so we're trying to figure out like how this noise in the solution affects our backpropagated gradient when you have a structured loss, means when your objective function has physics. And so here we see that we train our network for 1,000 epochs here for a one-dimensional Poisson equation, and we show the distribution of the parameters here on the top left. And then we want to perturb that parameters, and we get a perturbed state just to assess the impact of noise. And here we get our perturbed state, and we see that noise is not these two are acceptable. So noise level is not that high, and we want to now see how they impact the solution in the derivatives and the second derivatives, and eventually our backpropagated gradients. So you see in the bottom left that the solution at the perturbed state is not exactly matching the solution before that. And then if you go take the derivative of that, obviously because you have a noisy solution, then your derivatives would look worse. And if you go and take second derivatives, it would even look worse. And because of that, then your objective function would get noisy. And then we want to look at how the backpropagated gradients would look. And here, the bottom, we show the bottom left, we see that before adding perturbations, the distribution of these gradients are kind of like close or concentrated near zero. And that means that the model is kind of approached or converged, you could say. But once you have a slight perturbation in your parameters or a noise in your solution, then your backpropagated gradients are increasing 1 order of magnitude. That means that your model is getting updated with incorrect gradients, and that could impede convergence. This is severe for PIN approach because of the scale disparity, but for pecan model, we used pecan approach here to kind of not have that issue, but still we see that it affects the backpropagated gradients. And we also tackled this issue in our upcoming manuscript, and we show that this benchmark problem that was studied in van der Meer and colleagues, we show that you get 8 orders of magnitude better solution with just using one single hidden layer of their network. And this is another benchmark problem that was studied in Van der Meer and colleagues. And we show here that we use the same network and the same optimizer and stuff, and we get 2 orders of magnitude better solution than their method. And this is a benchmark problem that was studied in DT and colleagues. And so they showed that for convection problems, if you increase beta, then it would get harder to learn, and they used curriculum learning to do that. And so they trained, like, they started from a very small value of beta and they increased it to beta 40, and that's how they learned it. And here we show that you don't have to do that. You could just train one model by formulating it properly and constraining the boundary conditions. You could get like 2 orders of magnitude better solution with just training one model. And this is another benchmark solution that was studied in RDT, and they used sequence-to-sequence learning. And they showed that this could be learned with sequence-to-sequence training. And here again, we show that you don't need to do that. You could just formulate an objective function that's constraining the boundary conditions properly, and you're getting way better solutions. And we haven't published these things yet, but we're hoping to get it out soon, with the codes and the GitHub and all that jazz would be also public. And this is another problem that we studied. It's so this is basically a hot layer and a cold layer, and we have a vertex a velocity, and we're trying to see how that velocity, how these hot and cold fronts would get mixed. So here's a little simulation. Yeah, there you go. And that's it for me. Thank you. And this is the link to the published paper in the Journal of Computational Physics. It includes some of the stuff that I talked about. This is the archive link, and this is the GitHub link. You guys could fork it or download it. And if you have problems, you could maybe hit us up like this email address and ask your questions. We'd be happy to help. Thank you.
Thank you so much, Shams. Well done. Thanks a lot for sharing your work with us and for your very clear presentation. In the meantime, if there are any questions from the audience, you may ask in the chat, or you may unmute yourself and ask in person. In the meantime, I have a question, whilst maybe people think about their questions. So you mentioned you showed us how you tested your approach on a regular domain. I was wondering though, like in real world systems, the problem with measurement data is that it's not simply noisy, but it also has increased the spectral complexity is generally high, which makes it more irregular. I was wondering how because when you showed us the sinusoidal example, the spectral complexity in real world systems is generally high. It's much more complex than that. I was wondering whether this would your approach, how your approach would behave in such a scenario.
That's a good question. Let me go back to this slide where I showed my formulation. So we include measurement data in this loss function, which is calligraphic G sub m. And here we assume that if you have m number of measurement data, and so the noise or the error would behave like Gaussian, and so you would have this sigma there. And so here we don't assume that you would have different frequency in our measurement data, but that would you could add two different objective function if you do know that about your data. And if you don't, this should be okay to just have one objective function and one variance. But if you do know that your data has different variances and different scales, then it would obviously help to have different objective functions with different variants.
Like, is it possible perhaps to include an SVD kind of thing in this? So, when you do an SVD on spectral data, you can actually extract these frequencies. You can get.
I see. No, you can't do that. Here we're trying to learn the solution. So we're not trying to learn those what SVD is doing.
Right,
We're
right.
not.
Okay, thanks a lot. I have another
Thank-
question, but I'll leave it to the end. We have a question here from Tommaso, who asks, can you explain what's the definition of the three elements of the loss function for PECANN?
3 elements. Are you talking about this one?
Yeah. Sorry. Yeah. Can you go a bit deeper in the definition of the first one?
Oh,
So,
okay.
yeah, that one. Thank you.
Great. So here, we're saying that, well, you have an objective function for your PDE, which is a calligraphic F in this case, and also the measurement data. And so the reason we define our objective function like this is that even in conventional numerical methods, you're discretizing your solution. And so you're not enforcing the solution 100% on every point in the domain. So you say, well, let me discretize my PDE. So you're introducing truncation error and all that stuff, but still you're getting your solution. So, and you have variational formulations, for example, that that says, well, you don't have to strongly impose your PDE. That's why we said, well, let's minimize a loss function on the PDE, which is calligraphic G sub F. So this calligraphic G sub F is the objective function for the PDE. In case you have measurement data, you could add calligraphic G sub M, which stands for the objective function for the measurement data. And so here tilde U is the measurement data, and this U is the one outputted by your network. And this sigma is the variance of your data. And calligraphic B is the boundary operator. If you have, let's say, a Dirichlet boundary condition, then this would be like U minus U hat, or yeah, your labels minus that. And phi is a distance function. It could be an absolute value function. It could be a quadratic function. And so once you have this this constraint optimization written down, then you could use augmented Lagrangian to convert this constraint optimization problem to an unconstrained one, which is here. And now these lambdas would appear, these mu penalty parameter would appear. So we set this to a large number like 10 to the 4, 10 to the 3. That should satisfy, that should do the job. And these lambdas would get updated like that. This comes from the augmented Lagrangian method. If you go check out the augmented Lagrangian method, then you'll see that these lambdas are mathematically derived, and you have these formulations. And so now we're not heuristically or empirically updating these lambdas. These gets updated properly, and so the boundary conditions are constrained properly, and you also included the objective or the information from your measurement data and from your physics.
Yeah, thank you. So we can say that the contribution of physics is both on the first element and the third and the fourth, right? Of the Lagrangian of the loss function.
Yeah, if you say the boundary is your physics, sure. Sorry, but if you say, well, boundary is nothing but, because you have labels, you have data on the boundary, so it depends on how you define your physics. If you say that's physics, then sure. If not, then these are just your constraints.
Thank you.
Thank you, Tommaso. We have a question from David.
Thanks, Shams, for your presentation. I mean, I saw your work at the SciTech Forum, which I presented myself there. And so I was very keen to bring you over at our seminar. So thanks for this, and seeing that you have made some progress since then. I actually have two questions, if you don't mind. First, is actually from this first slide, from this slide you are showing.
Oh.
Actually, I'm curious about, obviously here, basically your Lagrange multiplier lambda is learnable, yeah?
Yes.
How is that, with this formulation you are proposing, do you avoid, obviously, do you avoid the optimizer converging to a lambda 0, which will be actually minimal loss function, no?
Oh, that's a good question. So these lambdas are not actually parameters of the network. So our optimizer is not updating them. What we do is we Yeah, our optimizer is only optimizing theta. And because we know the update rules for these lambdas, these are just another, like once you optimize thetas, then you update these lambdas. Yeah, and so we start these lambdas with 0, and we just do this with this update rule. So that's like a typical Lagrangian approach. That's how how people use it in that. And so we kind of like adopted that. Yeah. And because you have, so now here, look at penalty, the penalty. Oh, I think I missed to define the penalty here. So this pi is a penalty term, and this is a quadratic penalty in this case of the constraints. And so this mu is something, a large penalty like 10 to the 4. And because these are not 0, the objectives of these betas or the pi betas wouldn't be 0, because there'd be something positive. And so your lambdas would never stay 0, as long as you have some a penalty that's positive, which would occur with these constraints. And so if this is 0, that means you're satisfying the constraints automatically, like nicely. And so, you know.
But you're trying to minimize that, no? Because that's your loss function for the boundary conditions.
Yeah.
So are you trying to make phi 0, phi 0?
So phi is a distance function. So phi can't be 0. It's a function. Like here, for example, we started from a formulation like this. And here, calligraphic B is your boundary operator. And so you want the solution at every point to be within a small interval here. And now you could convert this to an absolute value and say absolute value of beta or B is smaller or equal to epsilon. You could do that. And we said, well, what if you use, instead of absolute value, a quadratic function? That will work too, because we don't care about how off we are. As long as we're very close to 0, we're good. And the minimum of, and so this phi is just a convex function, like a quadratic function or an absolute value function. And the minimum of this phi is the minimum of beta, the minimum of B. So that's, and that's how we started this phi. And here we showed that your phi, if phi is a quadratic function, then your gradients would always have this error term in it, and they would always backpropagate that information. Unlike if you didn't have, if phi was an identity function or an absolute value function. And in this case, these lambdas would never stay 0 if you're not satisfying your constraints. And particularly like when you're training your network, this operator would never be 0, because I mean, you're not satisfying the constraints like by default. And so, yeah.
I see now. So effectively becomes, goes towards 0 because when you are satisfying the boundary conditions effectively.
Yeah.
Okay, clever. And if I have time for this, I cannot see anyone else for a question. So maybe if I can ask my second question.
Sure.
Which is still a mystery for me. And I still didn't get a convincing answer, to be honest.
Sure.
As you know, PDEs and also ODEs, no? Okay, ODEs are the solution of the ODE depends on the initial condition. The solution of a PDE depends on both the initial condition and the boundary condition, yeah?
Correct.
I don't see how, how to avoid on a PNNN, or even in this approach with multiple loss functions, how you get the solution inside the domain be the one that, because obviously there are multiple solutions, no, of the PDE solution. So how do you get the solution inside the domain to be the one that corresponds to that for the boundary conditions? How do you, for example, I have had cases myself where I get a solution, I manage to satisfy the boundary conditions, but then effectively through the rest of the domain, it just reaches the trivial solution of 0 everywhere, which is also a valid solution for the PDE, but doesn't correspond to that on the boundary condition or on the initial condition.
That's a great question. Go ahead.
No, I was just saying, I still don't see how with these approaches you get the solution that corresponds to that on the boundary condition.
So that's a great question. Let me repeat it so I know, so I understand your question correctly. So you're saying that
Yeah.
You could have initial conditions and boundary conditions, and after your optimization is done, you're satisfying the boundary condition and the initial condition, but your solution is like a trivial solution for the
Yeah,
domain.
you're satisfying also the physics because you're satisfying the PDEs, but that solution doesn't correspond to the one that belongs with those boundary conditions.
Oh, so you're saying that your physics is satisfied, but the boundary conditions are not satisfied. Is
No,
that what
both
you're
are both are satisfied,
okay?
but the solution you're getting in the domain, which is found by minimizing the physics loss function, no?
Yeah.
That solution doesn't correspond to the one you get from the boundary conditions you have specified. It belongs to another plausible solution, but not the same to the not the one corresponding to those boundary conditions.
That's true. We haven't studied those kinds of problems, and I'd be happy to study or discuss it maybe. But what we do is here I showed only one boundary condition. If you have initial conditions, you could have another constraints for the initial conditions as well.
Yeah.
And so the reason we have the objective function for physics here as an objective function is that if you train it for a longer time, you minimize this thing, this GF, and because this is a non-convex optimization problem, then you could, what you're saying could happen, because then that would I think more speak to the complexity of training neural networks rather than the objective function, because you could land anywhere in the space of parameters, and that could possibly happen, that you get zero or maybe very small loss on your objective function, and the boundary conditions are satisfied.
Mhm.
I haven't came across one like that, but
Yeah.
I'd be very happy to discuss that, and maybe even if you know of any particular PD that you work with, I would love to try this on that and see how it turns out. But here, if you look at the problems, benchmark problems that was presented by Aditi and colleagues. So
No, that seemed to work. Yeah.
it works very well, and for this one as well.
Mm-hmm.
And so yeah, I'd be happy to work on PDEs, the kinds of PDEs that you discussed.
Okay. Yeah. No. I'm not questioning that the method doesn't work. I
Right,
just
right.
I don't understand how this is avoided. Oh yeah, how this.
You mean
how,
the trivial solution is avoided?
Well, how how to make sure, so how to get a connection between the boundary condition and the actual solution everywhere in the domain.
Yeah. So I mean,
But the way the loss function is written, they are totally disconnected effectively.
you mean
While in a
here?
finite volume scheme, basically, because you are propagating the solution from the boundary condition through the domain, no? In a finite volume scheme.
I see. So
In the
here,
loss,
I see. So in an objective function, you're saying that there's no step-by-step information propagation.
yeah, they have the way it's formulated. As I see it, they are disconnected, aren't they? Boundary conditions with the.
Yeah, and here we formulate the constraint optimization problem, but what we minimize with the network is this.
Yeah.
So they are connected. Like we do not train these objective functions separately.
No, I know. No, yeah, no, I understand that, but there is no connection. So you can get a neural network that could do very well for the boundary conditions and very well for the domain. Yeah, but the solution might not be the one that corresponds to the boundary condition. There is nothing linking that.
True.
Or maybe I'm not expert enough to understand this, but
could happen. That could happen. But the problems that we studied here are all well posed. So that means that if you have boundary conditions and you have one unique solution, and as long as your problem is well posed, you should get that solution that is a solution for your PDE. But if the problem is not well posed, then it could happen that you're getting like some trivial solution that's not the solution you're looking for. But all of these PDEs that I studied here are all well posed. So you know that they only have one solution.
Okay.
Yeah.
All right. Thank you.
Right. There's some feedback from Shamsulhaq, if I'm pronouncing your name correctly. He says, I don't think that there is any work on proving uniqueness of the solution obtained from neural networks.
Oh, yeah, sorry, I was just kind of, I think David's argument is that how do you know that the solution you obtain is unique, right? And I don't think there is any proof that neural networks, the solution that you get is unique from that perspective, like a mathematical proof of that stuff. But as Sham said, if you start with the well-posed problems, and then neural networks basically learns the unique solution. So, but why that happens, or there's no proof of that as far as I know. And Shams could comment more on that stuff, but yeah, it is something of a, I guess, challenge.
Yeah, so yeah, as long as you have a well-posed problem, then you know that the solution to this well-posed problem is unique. Then then your network is hopefully, after formulating an objective function that's properly formulated, finds that solution. But if your problem is not well posed, that means if you have multiple solutions for your PDE, then that could be problematic. Now, if your network is not converged, that would speak to the complexity of training neural network, not with the way you're formulating your objective function. Now, if you do not have a well-posed PDE, then it could be that your network didn't converge, or you're not getting the solution you're looking for. But that has to be discussed. That has to be, I think, investigated. And I'd be happy to work on those kinds of PDEs. You could shoot me an email.
Okay. Yeah, of course. Yeah, I can write you later on. I mean, I'm conscious also on that time, so I guess we should move on. Thank you for this, guys.
Thank you for inviting me. Thank you so much. It was great to talk here.
Thank you so much, Shams, and also thanks for provoking a good discussion. To everyone who's still in the chat room, yeah, please follow us for our upcoming seminars. And also, again, if you would like to contribute to the series, please get in touch with us. And for those of you who are not subscribed, you may do so again on the website, which maybe I should have posted here. I'll do that very quickly. Right. All right. Thanks again, Shams.
Thank you. Thank you.
Have a good
Thank you very much.
You too. Thank you. Hope to see you guys.
Thank you very much, everyone.
Bye, everyone.
Joining us. Bye.